So, thanks a lot for your patience. Today we'll be talking about exploitation and taking this beyond just X86 and ARM exploitation, and we're going to show you a new kind of system and basically compare this to ARM exploitation in the past. So, my name is Carel. I studied computer systems engineering. Basically, I taught programming for a very long time. And I developed some e-commerce applications over time, went over into teaching secure coding concepts, and then from there on, moved into security the last decade or so. And I worked with Philipp for a while at CompuSecurity, and currently I've moved on to finance in Zurich.
Okay, so my name is Philipp. I also work in the security field since like 5 years. I also do like beer, so after this talk I would enjoy a beer with every one of you. And yeah, we do this as a side project. So our day job, or my day job, is more like pen testing and doing assessments, more in the web application field. And we do this as a private research in somewhat like 2 hours a week. So we are always open to contributions, so if any one of you is interested into this, get in touch with us, and yeah, we would like to work with you.
Okay, so X86 exploitation and ARM exploitation, all of this has been done to death. You have courses available on this online, and a bunch of people have information out. A lot of books are available. And this isn't to say that these things are not interesting anymore. It's just that new systems occasionally pop up that might also be interesting to exploit. So occasionally these systems show up, and then we can go ahead and work with them. So if you bear with me for a second. We're going to talk you through basically 4 parts. The first part is historical exploitation, and then we're going to take you through to the mitigation factions. Then after we've covered the mitigating factors, we will give you actual examples of code comparisons, so we'll show you the assembly code for handling this and working with this. And then after this, we hope to go ahead and tie it all together and tell you where to go if you want to go ahead and explore Extensa exploitation. So hacking these small IoT devices. Okay, so in the shiny world of IoT devices, what we have available is essentially ESP32 devices and the 8266 devices. And these devices are very low power devices that provide you with Wi-Fi access and Bluetooth low energy. And both Amazon and Microsoft are now basically interested in this. They want you to feed the IoT sensor data into their networks, and they have provided IoT cloud solutions. This is very recent. When we started working with these devices, these cloud integration mechanisms were not available just yet.
So, but is security really a concern on those low-powered devices, apart from crypto chips for encrypting the flash or something like this, and transport security for your data? Now, it's not really, they don't really take it into concern because it takes CPU cycles to implement security, which is then affecting your battery life, and a lot of those devices run on battery. So, on this slide, we have a quick overview of some embedded operating systems and what security features they offer. They are all pretty much similar, and we start with, it's not working. No, I need the next. Yeah, we start with Zephyr OS and Linux. They both do mostly support the same security features, and we can see that ASLR is only supported on ARM. So right now, no one has implemented any ASLR for Extensa. There is some work on this done by Jos Wetzels, but not yet. So, and then we have FreeRTOS, and FreeRTOS is some kind of the super embedded system basically any low-powered system is using FreeRTOS, and it's not offering a lot of security features. It's also due to the limitations of CPU. You don't want to waste cycles on this. So yeah, it is not offering ASLR on any platform, but stack canaries and non-executable memory. But especially for Xtensa and ARM, this is already inherent due to the hardware architecture. And the hardware architecture of Xtensa and ARM, it's both reduced instruction sets, and they are implementing a Harvard architecture. This means we can access the instruction memory and the data memory at the same time. And yeah, this means we have this separated, and this is the stack is always on the data memory, and it's not executable. So what are they used for? Mostly, the ARM SoCs are mostly used in smartphones. Everyone has the ARM SoC running in his pocket, or maybe even on the wristband. And in set-top boxes, tablets, media centers, portable game stations, the Nintendo Switch is using an ARM CPU. And also a lot of embedded devices built on the ARM ecosystem, because it's it has a big tool chain. A lot of people have worked with it, and yeah. So then we come to Extensa, which is a relatively new processor architecture. It has been first mentions are like in 2001, where the work on this started. It started as a university project, and it's a highly customizable processor architecture. This means you can download a program where you can configure the whole processor to your needs, which is why it's mostly been used for cars and motion sensors and for digital signal processing. This means AMD is using this on all graphic cards for sound processing, so it's in every PlayStation 4 you have one Extensa chip. And yeah, in the last years, Espressive, a Chinese company, started producing the ESP8266 and the ESP32. And since then, they get more and more popularity in the IoT world, and there's a lot of frameworks. Espressive has the ESP IDF, which makes it really easy to get bootstrapped and develop IoT devices. So why do they use RISC? This is they want to have a higher code density. Higher code density means that less instructions are needed for operations, and we heavily rely on the use of registers, so we don't need to do stack operations. And the most interesting feature, and this is what we talk a lot about today, is the so-called register windowing. This also, again, increases the code density a lot, because we don't use any stack instructions anymore. We don't work with the memory like this. So, the instruction sets have different specific properties. Extensa supports two different word lengths of instructions, 16 and 24 bits. This is similar to ARM with the thumb mode, and it's also used to gain an even higher code density. This means we use less space in the memory due to less instruction usage, and this means in the end we use less cycles and less energy. And ARM also has some interesting other modes, like Jacel, where you can directly execute Java bytecode. It's interesting. I have read it on Wikipedia. I have never seen it implemented, but yeah, anyway. So
on a very basic level, for the software developers out there, what are we talking about when we're talking about a register? We're essentially talking about hardwired variables on your CPU, so you can think of it as that. And these hold two types of data. You can have numbers, or you can have pointers to other locations. So the CPU goes ahead and uses this to tell it what to do, where to go, how to compute. And as hackers, we want to be able to manipulate the registers in order to do both, which is manipulate the data and manipulate the control flow.
So today we look a lot at the two different ESP releases, the ESP32 and the ESP8266. And the ESP32 is configured to use the so-called register windowing ABI, which means we basically have a stackless architecture, and the instruction set is not even giving us a push and pop instructions. So on each function call, we rotate the window for local registers. So I go more detail on the next slide. This makes it, however, a lot harder to exploit. So we cannot just do ROP, because a ROP gadget needs to populate registers. It needs to increase the stack pointer afterwards, so we get to the next gadget or our arguments for the function call we want to do. And so it's right now, it's more or less impossible to do ROP chain as we know it on ARM, not on ARM, on ESP32 because of the register windowing. Okay, so this is because every time we return from a function, the window will be rotated of the current registers. And therefore it is trashing our stack, because the stack relies on the registers. If we change the register window, our stack is trashed and we don't see our data anymore. So the solution would be to use jump-oriented programming. So we don't use return gadgets anymore, we use jumps. And they don't trigger the rotation of the windows. Okay, so on the other hand, we have the ESP8266. It is not configured using the register windowing ABI, which is interesting because in the beginning we thought all Extensa chips are using this configuration, but it is not used because it's making things more complicated even for the tool chain. So your GCC has to be aware of this, and yeah, it still offers a high code density if you deactivate it. And the good thing is on the ESP8266, it's really easy to find ROP gadgets. They're even in the boot ROM, and so you don't have to really search long for this. There are some perfect gadgets, which we will discuss on some of the next slides. But anyway, let's go back to the register windowing. So, okay, so back to the ESP32. It has 64 registers available, but we only see 16 registers at a time, thanks to register windowing. So this means each function call can see 16 registers, up to 16 registers. This depends on how you trigger a function. So if you use the call for instruction, you only have 4 registers available, and so on and so on. So, but what happens if the physical registers, the 64 registers, are exhausted? This happens after you call 4 leaf functions. Then the next movement of the registers, so the physical registers are exhausted. If we then call another if function, we take the registers and put them onto the stack of the current calling function. This means if we return from a function, those registers will be recovered from a stack. And this we can manipulate. Next slide.
Okay. So to visualize register windowing, we drew these graphs for you. What you can see on the left side is that the frame pointer is adjusted on ARM systems, and ARM is not implementing register windowing like the Extensa. On the Extensa, on the right-hand side, you can see the register window is rotated or shifted, and we'll mention later why this complicates exploitation for us. It makes things a tad more difficult. So, what are instructions? Going back to making this easier for the software developers out there, we need a way to control the registers, basically the variables that we talked about earlier, those things that are hardwired. And so instructions are a means and a way to affect the data and to control the flow execution of a program. So affect the registers, affect the CPU state. So an attacker's thinking will always be, well, my other computer is your computer. So this is exactly what we're aiming at. We're aiming at controlling somebody else's hardware, those IoT devices with these chipsets. And for this, we need to understand the instructions for each platform. So now we're going to do a jump into the actual instructions for you.
So on ARM, we would, like I already said, we would just do a pop into a register and then a pop into the program counter, and we have basically a good ROP gadget. It's really easy, but this is not really possible. As you can see now, These are is like a small comparison between ARM and Xtensa, and you can see that there's no stack operations. There's no push and pop. So you have to take care of this. This is because they don't want you to use the stack. They want you to use registers. This is why they give you so many registers. And so we need to find gadgets which are using registers as the stack and adjust the pointer in these registers. So now we have talked about instructions, and let's see some actual code. This is just a classical, typical Hello World. And we compiled it for ARM and for Xtensa. And as you can see, especially in the Prologue and epilogue of the Extensa, you have only the instruction entry and return WN, which just means return window. So it's rotating the window, and you see there's no like stack setup, and this saves you a lot of instructions. You see the Hello World is only taking 6 instructions, where ARM needs around 9 instructions, because first the stack needs to be adjusted in the Prologue, and in the epilogue we need to recover the return value, and so this means that we have a really high code density, and it visualizes a bit more that you don't use the stack, or not that often.
So here we have a list of the general purpose registers and what you should be aiming at for in your exploitation. So what you'll see is, you'll notice that we have A0 to A16 on Extensa. We have a comparison for the program counter over there, and you want to be able to affect these in your exploit, so to change the data on these specific registers. And we'll show you some more code examples in a bit. So the only safe computer is a computer that is turned off, and this is especially true for IoT devices. The problem is that you always have a connected device. So the best we can do as people trying to keep things safe is to raise the cost for the attacker. And if we want to raise the cost for the attacker, we need to require more skill, more time, or more computation from them. So we try to implement a mitigation, and this raises the cost for them. Hopefully in this race of increasing the cost for them and implementing the mitigations, we win in that war. So depending on which side you're on the exploit side or on the defend side. So the first thing we have is we have stack canaries. So stack canaries provide a mechanism for us to detect when exploits are being run, when buffer overflows happen. And if I can get it to go to the next thing, ASLR introduces randomness that makes it difficult for the attacker post-exploitation to predict where the code will be running. So we take away the assumptions that the attacker has, and in this way we make it more difficult for them. The next thing that I cannot see on screen for a second is, okay, so non-executable code and data memory. So what we do is we separate this out. Is the section writable or is the section executable? And it cannot be both at the same time. So again, we make it more difficult for the attacker, because the attacker then needs to control, listen, is this writable or is it executable? Is it manageable or not? And then lastly, we have some other detection mechanisms that makes it a bit easier for us. Okay. So, and go back. Yes. So what we often see in technology, sorry about the over-scrolling, what we often see in technology is new attack vectors are being found, and as these attack vectors are being found, then the engineers and the protectors need to go ahead and they need to implement the mitigation actions for this. So this can happen in 2 places. It can happen in software, or it can happen in the hardware itself. And if you have a look at this graph that we drew for you guys, we start with basic exploitation mechanisms. So I'm going to step down for a second so I can actually see what's on screen. So we have stack canaries. Stack canaries provides you with the functionality for detecting if a buffer overflow actually happens. And it makes things a bit easier for us to say, okay, something wrong happened. Let's not execute this code because we cannot trust code anymore. And go back. I don't know why it keeps scrolling. Sorry, I have an oversensitive mouse. The next thing is, if we have a payload address and the payload address is predictable, we have a problem. Because the attacker knows where to go, to point the code to execute their code, and they can control flow. So in order for this to happen, they need to be able to find a payload address. If they cannot find a payload address, so if things are unpredictable, we break the assumption for them, so we raise the cost of the attack again. We use ASLR. Then if you inject shellcode, in the past, everything was running in the same space, but now we separate this out into executable and writable, so you can't do both at the same time, again, raising the cost. But then attackers decide, okay, well, if we can't execute shellcode, or if we can't write to memory and execute memory at the same time, what we can try and do is we can try and use code that exists in the system. So existing pieces of assembly code that is precompiled into something like a boot ROM. And this is where we have the ROP chain. And for that, we can go ahead and we can detect if a ROP chain is possibly being executed. So a ROP chain, to detect this, you look for short sequences in the code that always returns or often uses a return. So if you see this often enough, you know that a ROP chain attack is being executed. And this was fully successful until about 2011, when people decided, well, if you can detect it with often having returns in your code, then if we can't detect this, so if we use jump-oriented programming, then you can't detect the returns, because this goes away as a mechanism. And again, you increase the cost for the attacker. Actually, in this case, the cost is increased for the defender because we don't have a blue box here yet. There's no way to defend against this, that we know of, at least. So
maybe machine learning or something.
But there are other speakers for that.
Okay.
So we can jump next. While something like return to libc is powerful, it doesn't allow arbitrary computation in the context of the exploited code. So for this, an attacker needs to go to return-oriented programming. So good, generic, perfect gadgets are hard to find, and they're hard to find in the sense that no automatable tools currently exist that allow you to scan for perfect gadgets. So you can't just load the boot ROM somewhere and say, find perfect gadgets. You have to go and look for them yourself. So DIN-IMA and drop aim to defend against these ROP type of attacks. DIN-IMA basically detects the consecutive execution of small sequences of code, what I mentioned earlier. So if small sequences of code are executed and often have a return, and this happens a lot, then we can be sure that maybe a ROP attack is being executed. And then drop, as a defense, observes that a ROP chain typically has this fast return and is a standard mechanism for ROP execution. We go to the next attacker step, which is jump-oriented programming, or JOP. And this, if that loads, is a returnless attack. So we remove the return that is detected to detect the ROP chain type of attacks. If we don't have the return, you can't detect it, you can't mitigate against it. So this negates the reliance on the stack for the control of the flow of the program. Where we had return to libc in the past, for attackers to jump to a specific system call, that went away because the compiler doesn't create that in the code anymore. People went and said, okay, well, what if we reuse existing pieces of assembly? Then ROP chain developed. And when people started defending against this with DIN-IMA and drop, then JOP removes the return requirement, and if you don't have the return requirement, you can't defend against this. Again, you can go ahead and you can exploit.
There's also really nice papers on this, so we will provide links afterwards via Twitter. There's some really good research on job chains, on ARM especially, so I can recommend it. So this is, I hope, the last return-oriented programming slide. And I think Carel already covered most of this. I just want to add, there is software which can build job chains already for you. There's the tool ROP Gadgets by Jonathan Sawalman. And there's the implementation of finding job gadgets for MIPS, X86 and ARM and even Spark, but not yet for Extensa because it builds on the Capstone engine and it does not have support yet for Extensa. But there's other tools you can use, and we will show this later.
So, what do we have when we're talking about exploitation and stack canaries? Stack canaries, it's something useful for developers because it's a compile time mitigation. It basically happens from the compiler, so you don't have to go ahead and change your code. You don't have to change anything. So, in the embedded world, and we jumped again.
The slide,
sorry. Excuse me, my mouse is hypersensitive today. So this is implemented on the compiler level, and the implementation is quite simple. You have a normal function, and a random value is put onto the stack. When the function returns, the epilogue is checking if the value is still the same. If the value is not the same, an exception gets triggered and then returns. So essentially, it's a safety mechanism to detect, has anybody fooled around with the stack or not? Okay, so the canary in the coal mine, that's basically where the name comes from. So this adds, unfortunately, it increases the code density. So the benefit you have of working with assembly is that it decreases the code density, especially for these devices, these IoT devices that need to be low power. And now, with a protection like this, we add 3 to 6 lines or 3 to 6 instructions in each function's epilogue and prologue. So we load the canary, we do the comparison, and then we branch if things were tainted, so if something went wrong.
So for the hello world, it would be double the instructions if you implement this.
Yeah. So I'll try and work with, there we go.
Okay, this is really just a quick walk over the address space layout randomization, which we don't see a lot in the embedded world because this is adding too much complexity, and complexity means that we consume energy or CPU cycles, and therefore it is heavily used in the smartphones. So if you look at your iPhone or at Android, ASLR is all over, but if you go to smaller devices, tiny devices, which are not allowed to consume a lot of energy, or you don't even want to do this because you need fast computation, especially if it's digital signal processing, you don't want to add instructions. So the randomly rearranging of address space allocations is just not doable on really smart, small embedded devices. So there's the solutions for this. We've seen so far, for example, this is a good example, is the BSD kernel, which is doing address space layout randomization for the kernel binary at boot time. So there's Jos Wetzels implemented this for, I think, for the STM architecture on Zephyr OS, but there's nothing like this yet for Extensa, and also most ARM systems, the smaller ones don't do it, so my watch is not doing this. So there's not any implementation of ASLR for Extensa, and if you Google ASLR and FreeRTOS, good luck, because you also will only find people searching for this and not implementing it. So if you have some time, maybe implement ASLR for FreeRTOS, but make it powerful. So memory can either be writable
or executable, like we said earlier, but it can't be both at the same time. This approach was first adopted by OpenBSD 3.3, and then later in Linux, implementations followed, like PAX and Execute Shield.
Okay, so let's look at actual simple exploitation. So this is like your 101 buffer overflow. And I took the Extensa setup with the registered window ABI. So this is special. It's a lot like Spark, where you also have the register windows. And this means you need to exhaust the physical existing registers before you can do successful exploitation. This is why I did so many leaf functions, calling the next and calling the next. We have so many levels, because otherwise it just would raise an exception that you try to access memory, which you're not supposed to do. And then basically if you use the FreeRTOS, the system will reboot. That's it. Nothing will be triggered, just a reboot. So you can do a small denial of service, but that's about it. So, but what happens if we have exhausted all the physical registers? I like to sometimes call them shadow registers, because you only see 16 at a time, at maximum. So on a return, the window underflow exception is triggered. You can look this up on GitHub in the FreeRTOS repositories. It's a really simple code. It's really detailed. You can directly see what's happening, but it is basically taking a stack register. This is most of the times register R5, and it's reading the register values out of this stack, which is stored in this register, and is putting the single registers back into where it was before, so before the function call. So we don't need to think about having really 4 leaf functions, because if you have FreeRTOS running, you already have a running network stack. And yeah, basically you have the thread management, and the first function you call is already more than the 4th leaf function of anything. So this is not really a concern, but you need to know it if you build your proof of concept code. You need to know this, because I was writing this bare metal, then I was like, oh no, it's not triggering, and then I found out, yeah. So I first need to exhaust all the registers, and this happens with the window overflow exception. So, so what's happening exactly? As always, our string is writing over the allocated stack size, and what's happening then is it's overwriting the registers, which are stored after the allocated stack. So this means we can manipulate what will be recovered on the return, and therefore we can get full control over the execution flow. On ARM, I don't have much to say about this. The function epilogue will return. We have overwritten the return value already. This is simple 101 exploitation, but for Extensa this is interesting, because you have to work with this window underflow exception handler. Okay, I don't think we can show the demo with the setup here.
No, you can. Just take the mouse and stand in
No,
front.
make it.
So we can't actually see what's happening on screen here, so I hope the switch is for us. Otherwise, you need to give us a second.
It's here.
So it's on this screen now.
Yeah, that's good.
Can you see it?
Yeah.
Now,
Just click. So this is really simple. What you will see here is just triggering the code we had before. And what you see here, it's returning over and over and over and over. This is because the return register underflow handler is always recovering from the same fake stack we gave him. So because we did not add the gadget which is increasing the stack address. So it will always return from this. Yeah, so also you can see a bit of debugging here, but I will show this in more detail later, because this is by far the most important thing. If you do embedded exploitation, you need to debug it.
okay, so you need to tell me if the screen is switched.
Oh yeah. Yeah, that's good.
Okay.
Next slide.
Okay.
So, but nowadays exploitation is not always that straightforward, and we cannot just jump there. So we will do even more ROP chains, which, okay, yeah.
So again, I'm going to return to the narrative that I had earlier, which is we have an arms race. We have exploits and we have mitigations being implemented. So non-executable stacks were safe until someone discovered return to libc. That allowed you as an attacker to basically jump to a part of the C libraries that were already on the system. You could simply jump to an existing function, but this could be protected against. Stack protection mitigated against this, and we couldn't execute this type of attack anymore.
Okay, so back to return-oriented programming. Why do we need to do this? Because the stack is not executable. I hope it's the right slide. Yeah. Okay. We even have this as hardware feature nowadays. So the instruction memory is separated from the data memory. And so we need to reuse the instructions, as Carel already told multiple times. By chaining multiple gadgets, we can do different things like copying shellcode to executable memory, which is what we want to do on Extensa. Or calling functions to, for example, mark areas as executable, as you would do on ARM on Linux. So you use mprotect to basically set your stack as executable after you put your shellcode there. So yeah, on Extensa with the registered window ABI, this is not really so easy, and we will demonstrate this on the next slides. Right here, I hope it's the right one. That's your typical ARM ROP chain. Basically, you just prepare the values for calling the function mprotect and then jump to your shellcode. It's really simple. You just need to know what to do, and you have to bypass some null bytes. That's why we do the trickery here. Yeah, okay. So, next slide. So this is what the ROP chain looks like on Extensa, but without the register window ABI. Because we don't have return instructions on the register window ABI, but I still want to show you this because it's possible on the architecture, but the code is not generated if you have the register window ABI active. So this is populating registers, and then it's just writing what we have. We have more detail on the next slide. Yes, I show you the gadgets in detail now. So.
Okay, so this took me a while to understand, and we need to actually speed this up. I think we're running towards a close. Essentially, gadgets need to exist in the boot ROM, so we need to find them in existing code because we can't really plant stuff there. And you need to find this in pre-existing assembly code. Ideally, everything should be in the boot ROM and ready for your use, but this means you have to go and find them. Can you find specific functions for loading, storing, moving? And if we can find this for reuse, then you have a perfect gadget. If you can chain this, then you have the ROP chain that he keeps rambling about. Okay.
So what are these gadgets doing? These are exactly the gadgets you saw on the slide before, just a bit more visualized. So we first populate the registers A12 to A15. Then in the second gadget, we take the contents of the register A14 we populated before and put this at the address stored at the register A15 with the offset 60, but that's not important. You find other gadgets with other offsets. And then we just sync with the instruction memory. This is needed because you need to flush your memory writing before you actually can use it. If you jump directly there, it will not work. So, and for the ESP32, currently we are still searching for the perfect gadgets. We right now have a few gadgets where we can chain like multiple calls, but it's not yet Turing complete and we cannot really move memory areas. So we can work with some registers, we can increment the stack already, but it's not 100%. And we want to find this in the boot ROM because this is on every ESP. So this makes it a bit more hard, but it's only 2 megabytes of code. But yes, we will talk about this in future talks a bit more. once we have the complete, fully working registered window ROP chain. But if you want to work with us, we share all the information. So yeah, just to speed this up a bit, we use the Radar 2 for finding the ROP gadgets. There's also implementation for Extensa by Joe Sandin. It's called XROP, but I use Radar. It's a bit slower, but it's a really nice reverse engineering tool, and the ROP gadget search so far was really helpful for me. Okay, so this is again a small overview just to visualize the difference between the call 0 ABI, so not using register windowing, and the register windowing ABI. These are both the same function taken from the boot ROMs of the ESP32 and the ESP8266, and you can already see that it's a lot bigger. And in the Prologue, you can see that the stack pointer is adjusted, and on return, the stack pointer is recovered. And on the ESP32, we simply do entry and return. That's it. Okay, so yeah, debugging is really painful if you do it on real hardware. As you can see, I cannot solder, so I use paper. And yeah, it's really painful. You have to find the JTAG attach points, then you have to configure OpenOCD accordingly. If you don't do it right, you will get basically crap. And then you need to connect the GDB to OpenOCD, and then you can set breakpoints. But on Extensa, you can only set 2 breakpoints, which is basically useless. And so I also have to take care of the cables. A lot of time when I was debugging the cables, because I did not solder them, went away. So I went to search on Google, and there's a project called QEMU ESP32, which is really a pain to set up. But after you have it set up, you just connect the GDB, and you can set as much breakpoints as you want. And another important thing, if you start to debug on Extensa, is configure FreeRTOS to only use 1 core. Then it's easier to follow the jumps through the functions. Otherwise, you will jump between the cores. So you have the network handling core while you do stepping. And you want to step through a function, not to the network handling code. You don't care about this. So, how much time do we have left?
I think we jump over this. Okay, now we do it then. The
yes.
demo.
Okay, I have a quick demo showing this. It's really quick, so. Yes, okay, so what you see here is you have down here, you have the OpenOCD, which is connected via JTAG to my ESP32 device. The green text on the upper corner, or now the white text, is just a console output of Mongoose OS, which is a really nice framework to develop Extensa-based projects, or basically IoT projects. And on the left, you can see debugging. You can set the breakpoints and so on. So this is really helpful to get you started. And I also can recommend to use the GDB dashboard, which is what I'm using here. So you can directly see the register contents to have a quicker overview. So yeah, that's just a quick walk over the. You can close it. You can close it first. Yeah. Okay. Is it the right side?
Nice. Okay. So what's actually next? To hopefully inspire some of the students here, we went from zero knowledge about this architecture last year, March?
Yes.
Yeah, last year, March. We had zero knowledge about this. We started cracking open the manual, which is a 700-page tome of assembly, which is quite daunting. Philipp reads this at night before he goes to bed. I try and stay away from that and stick to the hacking parts. So grab yourself an Extensa. An Extensa chip and development board cost you something like $5, $6. So it's really easy to get. You can order them on Ali. Do some research on what devices actually use this. So there's a myriad of devices. I don't know, ABS systems, the Nintendo Switch?
Nintendo is not using it. AMD is using it for sound processing.
Okay. So sound processors, I'm giving you false information here, nice. But find out what devices you can hack this on or what it exists on. Don't believe me, do your own research, and then go ahead and break stuff.
Also read the code. Read the code of FreeRTOS for Extensa. This will teach you a lot, more than the manual section.
Yeah.
So.
But you can go from 0 to very interesting knowledge about the chip, the architecture, debugging, etc. if you do this in your own time. Go and have a look at this video. This was on Hack of the Day about a week back. It's pretty interesting because with only 2 pins on the Extensa development board here, they actually create composite video from this tiny little chip that's very low power. So, very cool project. And then I would like to extend our thanks to people that inspired us. The first person is Joel Sandon, did some very good initial work on ROP chains about 2.5 years back. Samuel Shah, Philipp attended his ARM exploitation courses. Jos Wetzels, very interesting guy to follow. He's implementing some of these mitigations on low power devices and trying to keep the code density low. Then we'd like to thank Arun for convincing us to submit for the CFP and flying all the way here. And then we'd also like to thank our employers and our colleagues. And lastly, we want to thank you guys for taking the time, sitting through an hour of tense presenters on stage with technical overscroll difficulties and the like. So if you want to get in touch, the top one is Philipp. The middle one is me. The bottom one we put on every presentation we give, but I'm not going to tell you why. So, questions and answers. We have some stickers to hand out and some non-Swiss chocolate, if you're interested, if you ask a good question. Sorry, some of our stuff was confiscated at Mumbai airport, so we settled for second best. So, any questions?
So I remember seeing when you're talking about the chemo image, you wanted to compile it with 1 core. Any reason for that?
Yeah, it's not for the QEMO. You go to the FreeRTOS examples, which are in the QEMO package, and there you do a make menu config. And there you can select using 1 core. You can add some debugging options. So it's like compiling the Linux kernel back in the days.
Yeah, right. So I'm just wondering why 1 core and not more than that. Any reason?
Yeah, okay. I might have explained it a bit weird. So it's so if I set 2 breakpoints, for example, in the beginning of a function or at the end of a function, I want to step through the end of the function. And the problem is if you have a dual core system and do on-chip debugging, it will jump. It's not even another thread. It will jump to the other CPU core. And so even if you do just step in your function, you will end up in FreeRTOS network handling code. And this makes debugging basically impossible. This is why I recommend using QEMO and also compiling this with only a single core. Then you have threading, and you can set the thread you want to debug with GDB by that thread and the number of your thread. So that's why.
I have a couple of more questions if you don't mind. So we had issues with speculative execution on X86. So what is the, is there any chance of that happening on Extensa?
Yes, it is, because it depends on how the processor is configured. There's a configuration file, and you can enable speculative execution on Extensa. But on the ESPs, it's disabled. For ESP8266 and ESP32, it's disabled. I checked this especially because I knew someone will ask this. But yeah, you can enable it, and then you could try to do this, yes.
So are you still using Tomasulo's algorithm for that? So are you still using Tomasulo's algorithm for that, for speculative execution?
I don't use anything with speculative execution.
Oh, okay. Right.
AMD processors, so. Any more questions?
So actually we have some Linux implementations running on ARM processor. So
Can
we
you
have
speak a
some.
bit louder? I cannot understand.
Can you hear me? Yeah.
Yeah.
We have some Linux implementations running on ARM processors. I would like to know what are the defenses against ROP and JOP in this. Are there readily available implementations that we can deploy?
I don't know about those mitigations. He looked at those. I don't care about mitigations. I just use JOP. So
ROP, there are no implementations which actually defend against ROP as of now on Linux.
I don't understand the question. Sorry. Do you?
I wasn't listening. I was
Okay.
Okay. So,
Sorry.
do we have any readily available solutions to defend against ROP on Linux implementations?
On Extensa.
On ARM?
Yes, on ARM there's, I think it's mostly research right now, so I don't know exactly if there's something available. My focus in the last year was mainly on Extensa, and there's nothing available, not for ROP and not for JOP, which is mostly because no one is doing exploitation on Extensa so far. But I hope after this a lot of people start doing it, and then the security features will come, I hope. Because FreeRTOS is now Amazon project, but so far they did not do really much security mitigation implementations. So they only have a really stable operating system which has been fuzzed a lot. So I would say it's a pretty secure operating system, but it's not adding exploit mitigations because exploiting on embedded devices was not so interesting. But it's getting more and more interesting because we have a fridge, we have mobile phones, we have everything is connected to the internet now. And the smaller it gets, the more vulnerable it is. So you won't mind Bitcoin on this, but you can abuse it for DDoS attacks or other stuff, spying on people. And yeah, so it will come. It will be.
Do we have time for another question?
Thanks.
Yes? Okay. Over there.
Okay, so in Extensa is actually a stackless architecture, okay. And in slide 16, you have mentioned stack pointer over there. So why we use stack pointer as Extensa is a stackless architecture?
You can use a stack, but it's not. You don't have your typical stack where you have the push and pop instructions. So this is what I mean with stackless. So for your function calls, instead of putting all the arguments on the stack, you use the registers. But you can build something like a stack, which you need for basically every bigger data set, which you cannot fit into a register. You need to use a stack. And there's also a stack pointer, and a stack is definitely there, but it's not recommended to use it. That's why they have the register windowing. They want you to use local registers instead of a local stack. That's all. That's why we call it stackless.
Okay, good. Thank you.
On that side?
Hello? Yeah, so we use egg hunting, right, for ASLR and egg hunting kind of techniques. So can we use it in Extensa or?
Sure. If you leak pointer information, addresses out of your program, if you can do this, you can bypass ASLR, yes.
Okay.
The same techniques apply. It's still a C program you exploit there. So.
Okay. Okay, thank you.
I have been using ESP with Arduino quite some time. Are there some methods to ensure that it is not getting exploited?
If I still enjoy it?
No, are there some methods to ensure that it is not getting exploited somewhere else? Because I have been using ESP8266 with Arduino.
Yeah.
So are there some methods to ensure that it is not getting exploited?
Not really. It's the same as on your PC. You cannot be sure if it's compromised. But there's one good thing on the ESP. You can configure it using secure boot, which will at least kill persistent infection. If some botnet will own your system or your ESP, it cannot get persistence if you enable secure boot. If not, we did a presentation at the dev camp. There's one slide which is showing you can actually write to the ROM of the ESP8266 and the ESP32. So then you cannot make sure anymore because your main functionality is still there. You will never notice. So there's no monitoring tools of CPU usage or something like this for Extensa so far. So if you implement this and do monitoring of your CPU usage or memory usage, you might identify that you're infected or exploited, but otherwise your device will crash, reboot, and you never know. So,
thank you. One last question, and we break for lunch. One.
Okay, and also I want to show you, if you want to join the CTF, we do the Hacky Easter challenge. You can go to hackinglab.com and solve some puzzles, if you want to.
Yeah, so I've been trying out heap-based exploitation. And is there any difference on heap-based exploitation, and is there any special mitigations on Extensa?
On Extensa, there's no mitigations so far. So
it's basically the same as any.
Exactly. Yes. Yes. And also, no, there's no mitigation. So you don't need to take care of this.
So some people are doing some work on basically not affecting the code base too much. But I would suggest having a look at Jos Wetzel's work. He's doing some work on mitigation, at least for free RTOS-based devices. So, yeah.
Thank you.
Now we are done with questions, and if anyone has questions, you can do this offline. And now we officially break for lunch.
Thanks a lot for joining.
Yeah.